Let's start. So first of all, let's check if you have any questions for me. Did you start doing the homework? How is it going? The first homework is posted. You can find it on icon. It states all the questions you need to do. Make sure to solve all of them and explain how you solve them. Okay, number 10 on section 1.2. Give me 1 second. Grab my textbook. Yeah, so in order for system to be consistent, you need to make sure that system is satisfiable. That means there is an assignment which is going to satisfy it. One of the ways to do it is to write all of those as logic propositions. So you're going to state that the system software is being upgraded is going to be P. Users can access file systems Q. What else can I see it? Okay. And users can save files R. So you have three, I believe, propositions out here. And now what you can do is literally you write them out as propositions composed statements, and you check if the sum of the assignments, the system is going to be satisfiable, meaning it's going, all of them are going to give you true. So you need, if P, then not Q, for example, to be true. So each of those propositions has to be true. And you can put it into a large logic statement, and you can do the tree table. You do not need it to be tautology. Now, in order to prove that something is tautology, we have discussed it last time. To prove a tautology, meaning we need to prove that for any assignment, you have true. So no matter what values, for example, P and Q take, the statement is still going to be, the composed statement is still going to be true. So tautology meaning always true. Okay. Well, if you want me to look at what you have done and check, like, and discuss specifically your solution on how you're solving something, please stay for my, like, go to a different link, but stay for my office hours after the class and we can discuss it. 1.2, 44. B. So I cannot go over 44B because it's an assignment, but we can do something similar. So if you're going to do something like number 45, for example, and I'm going to start sharing my screen. Here we go. So if you're going to have something like that, I'm doing 45A, P, Q, R. So what happens here is this is a node, so you're going to get a node R over here. This is an OR, so you're going to have Q or node R over here. This is AND, so you're going to have P and Q or node R. This is not again, so you're going to have, oh, this is not, and this is not. So in here, you're going to have not on this whole sequence. So this is the output of your gates. So those logic gates are output of not parentheses P and parentheses Q or not R. So pretty much you just need to pass the value through it and let me know what type of output you're going to get. And now we are going to talk about distribution and different type of things today. So there is no XOR gate symbol, but you can represent, we're going to talk about it. XOR is equivalent. You can write it as combination of OR and ANDs. So generally XOR is just a combination of OR and ANDs. 1.3, question number 20. What do you want? 24. In order to decide if something is logically equivalent, so for example, number 23, and yeah, I never do homework assignments in class. I can do something similar or explain something similar, but I cannot do the homework question because this is what you're supposed to be doing. So what you need, for example, in 23, you need to show that not P by condition Q and P by condition not Q are logically equivalent. This is actually the same as saying not P by condition Q and P by condition Q by condition over here, but this is tautology. So how can you do it? What you need to do is you need to generate a truth table. So you're kind of going to do P, Q, and then you're going to do not P by condition Q. And then you're going to do P by condition not Q. And then you're going to do the last by condition. You want to see all T's over here, all T. That's what you need to do. Then they're going to be logically equivalent. If you're not going to see all T's, then we have issue. So how can you do it? You just write traditional truth table. Hopefully that you're already all used to doing. So not P, false, true, false, 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 true, 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 false, false. And then by condition P and Q, not Q is false, so true, false. Wait, what am I doing wrong? Am I doing correct question? Yes. Not P, P. Yes, I'm doing it in opposite. So not Q is false. So True by condition false is false. True by condition true is true. False by condition false is true. And false by condition true is false. Now it's better. And then false by condition false is true. True by condition true is true. True by condition true is true. And false by condition false is true. So this way we get yes logically equivalent. Okay. Now, why does the tautology signify equivalence? So what does it mean to be logically equivalent? That means that if one thing is true, then the other thing is true too. And if a thing is false, then the other thing is false too. So meaning they take the same values. By condition table tells you it's true if both parts of true or both parts are false, which is logically exact same thing, saying this is going to be tautology for everything. Okay, so this is why they're logically equivalent. Okay, other questions? Great, let's move on then. So, let's see, where are we? So last time we talked about the tautology and we talked about contradiction, just reminding you contradiction is going to be all false, always false, not satisfiable. We have talked about how to generate a truth table. So last time I created a large truth table for you. And today we're going to be talking more about some of equivalent statements, and we are also going to talk about some of the laws. So I'm going to start with something some of you might already heard about. It's called De Morgan's rules. Okay, or laws. What it says, yes, we're still in section 1.3. If you have not of P and Q, it is logically equivalent. So this sentence over here, logically equivalent to not P or not Q. So this brings us to the question of how the knot is distributed. So originally everybody thinks that if I'm going to say no on both sides, then the sequence is going to be equivalent. However, logically it's not true. What really needs to happen and is besides distributing the knot, you also need to swap or and places, okay? So this is what De Morgan says. It says, if you want to distribute a knot, what you need to do is you need to put it on both sides and you also need to flip the sign. Now, during this course, we're going to be talking about De Morgan rules with different content. So we're going to be talking about De Morgan rules with respect to logic operations like right now. And then we're going to be talking about quantifiers, and we're going to talk about De Morgan rules for quantifiers. And then there are like De Morgan rules for sets and much more. So pretty much we will be covering De Morgan rules in many different sessions. But the idea is always the same. Distribute the knot and flip the sign. Flip the sign is going to be the main thing. So and becomes or, And if you have, oops, and if you have not P or Q to distribute that, you're going to do the same thing. You're going to distribute the not and you're going to flip the sign. So or will become and will become or. Let's see why it works and how it works. So in order to see what they're really equivalent, what we can do is we can say, let's look at P or Q. So true, 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 false, false, true, false, false. The or is going to give me true everywhere, but not the last line. And now if I'm going to do the not on it, we're going to get false, 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 true. Now what I want is I want to check if it's logically equivalent to not P and not Q. And in order to do it, we will need the not P and not Q, of course. So false, 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 true, true, false, true. And then now I'm going to do the and on it, which is going to give me false here and false here and false here and true here. And now what we want is we really want to look if this one over here is equivalent to this one, logically equivalent to the one over here. So I need the bicondition of those two lines. So false by condition false is true, false by condition false is true, false by condition false is true, and true by condition true is true. So we have a tautology, meaning they are logically equivalent. Okay. Now, the Morgan rules are very, very common, very easily breakable, and used in real life a lot. So many times you're going to be asked for something like, during a programming question, for example, you need to decide if the value of something is not between, like if x is not equal to 3 and x is not equal to -5, you want to do something. And then people will try to change a little bit. How do I write it, for example, inside the loop or as a condition in an if statement? And as you do it, you try to just flip the and or distribute, but you're forgetting when through De Morgan's rule, you need to do both and you need to flip signs everywhere. So a lot of times people are going to start with not equal here and not equal there, and they're not going to flip and then or, and then they're looking at their if statement or loop statement, and it's not working. And I don't know if it's ever happened to you and if you already took CS1 or not, but I know it's extremely common mistake generally when you write those conditions for checking for the range of numbers. Okay, next. So next, what we are going to do is I'm going to show you a table which can be found on page 29 of our textbook. And in here, we have two tables. You do not need to memorize them in any way. However, some of them you'd better remember because they make your life easier and they kind of supposed to make a perfect sense. So if you're going to think about it, if I have P and the true statement, those are like logical laws, there's tons of them about what is equivalent to each other. But think about it. If I have a statement and I say and true, correct? then this statement is going to be equivalent to just P itself. Why? Because if P is true, then you're going to get true. If P is false, you're going to get false, correct? So pretty much this true doesn't really make any difference. So you literally still have the P itself. So P and true is always going to be P. Similarly, P or F. If P is false, you're still going to have false here. However, if P is true, it's still going to be true here. So it takes an exact same values as just P. And it's easy to see if you put it inside the truth table and you just compare the P column with P or F column, you will see they're having the exact same values. So similarly, if you have P or T, it's always going to be truth, because for something to be true, you just need one of the OR sides to be true. So it doesn't really matter what type of values P takes. The statement P or true is always true due to true on the right side. Similarly with P and F, no matter what values of P you're going to get, either true or false, the false is going to win. It's always going to be giving you false, correct? Because for AND, you need both sides to be true to get the true value. P or P is equivalent to P. P and P is equivalent to P, so you do not need to have it twice. You can kind of drop it. If you're going to do the double negation, so not P, it's going to have an exact same values, logical values as P itself. Now, the order is not important. So if you have P or Q or Q or P, you're going to get an exact same thing, correct? They're going to take exact same true, false values. Same P and Q, Q and P, the order is doesn't matter. It's called cumulative rows. We have them for addition and multiplication. So in here, order doesn't matter, correct? Now, the associative law is also saying that if you have two ORs or two ANDs, the parentheses are not important. You can either put them on P or Q or R. It doesn't really matter. The order of operations here does not matter. It's kind of like a plus pretty much for us. Similarly over here. Now the distributive laws have similarity to our multiplication and addition. It's and not as kind of like a minus sign. So it does have similarity to traditional algebra. So if you have P or Q and R, you need to distribute the OR, and you're going to do P or Q, P or R, and you put AND in between the two. Very similar with AND and OR, distributing AND is going to work in the same way. Parentheses, you need to AND it with both sides and then do the OR of it. Those are the De Morgan rules. We spend a special time on them because they do show up a lot. The absorption rule. So in here, we still use, here we used P, Q, and R. R was different. Now we just use P, P, and Q. So P is used twice in here. And what we have here, interestingly, is if you have P or P and Q, you're going to get P. And it's interesting to see, you can kind of check it, all of it. Those logical equivalences, you know how to check them. You do it in your homework too. You just check that the truth tables takes the same values, correct? So biconditional is true for all of them. So this is how you prove all of those roles, but you can check how it absorbs it. Now, if you have P or not P, it's always going to be truth. And if you have P and not P, that can never be true. So you can never have both P and not P being true at the exact same time. This one is always false. So as you can see, this is like, those are the common rules of how you can play with your propositions and simplify them. We have two more out here. Those are more complicated because they have combinations of implications. And so you have P implies Q here, and it says that it's equivalent not P or Q. And we again can show it using the tables. We can also show different equivalences using the table rule. So if, for example, we decided to memorize all of those logical equivalent things, later what you can do is you can, when you see something large like that, you can really replace it with this and say they are the same. But in order to do it, you need to memorize all of those laws, which generally nobody does. But you can always check what it's close to. So if somebody asks you to show something using the table, this is how it goes. So I'm going to do an example for you how to use those tables. So assume I want to show not P by condition Q and P by condition not Q are logically equivalent. So first of all, remember we just did this question using the truth tables, correct? Remember we quickly draw a truth table. But I can do similar thing using those laws. I just need to figure out which ones to use. So what we're going to do is we're going to start with not P by condition Q. And I want, using the table rules, somehow to get to P by condition not Q. And the way I'm going to do it is I'm going to be using, okay, come here. I'm going to be using table 8. Using table 8, rule number 2, I see that P by condition Q is the same as negation of both sides by condition. Do you see it? So if I negate both sides and by condition using that rule, it's going to be the same. So I'm going to be saying it's logically equivalent using table 8, rule 2. I can say that it is the same as not P, implication not Q. Agreed? And now I'm going to go back to my tables, and I do need those tables because we didn't realize it yet. But we know that not P twice is going to be double negation law. So not P is equivalent to P, and it's called double negation rule. So in here, I can say using double negation. Oops. Rule, we're going to have P implies not Q because not P is cancelled. This one was easy. 2 rules and we are done. Sometimes it takes longer. Generally, you need to remember that if you want to prove logic equivalences, you have 2 ways. One way is a truth table, and generally this is the way most people pick it up. However, the more advanced you're in mathematics, the more often we remember those rules just due to the fact that we see the similarities between algebraic operations and everything. So it's important to see how we can also do it using the tables. So what we are going to do over here is I want to show that not P and P or Q implies Q is tautology. So one way to do it is just to draw a long operation table, correct? Like a truth table, right? You can do it using truth table. The other way is to try and manipulate it using laws. So let's see what laws can I use. First of all, I do see that I have P here and P here. So the very first rule I'm going to be using is going to be my distributive law over here. And I plan on distribute things and see if it's going to make my life easier. So to distribute it, I need to apply the first operation on both and put this operation in between. So let's do it. On a homework, you can do it either way unless it specifies. Sometimes it's going to say use like a truth table or use those equivalences. So either way, yes, you can do it either way. So now I'm going to distribute it. So using the distribution, I'm going to have not P and P, or not P and Q implies Q. Now, can somebody suggest me how I can make it similar, but what can I use now? What can you tell me about not P and P? Yes, not P and P always false. So what I really have here is I have false or not P or Q implies Q because of the rule that P and not P is false, and it's called negation rule. So we're going to say negation. Okay. So now the next thing is I have false or something. And when I have false or something, okay, so 1 second, we have oh, yes, you are right. Over here, we distribute the and. This one should be and. And thank you for those who have seen it. Yes, it is an and. Over here. Yes. Let's double check. Yes. So thank you. Yes, that was just, me writing too quick. But to distribute it, it is and on both parentheses. So now we have false or something. And using the independent rule, here it is, not independent, yes, identity laws, you're going to have P or F or P is always just P. So what we can do here is we can say using identity, you're going to have not P and, okay, yes, this is exactly how it works. Not P and Q implies Q. That's all I got. So my equation is getting simpler. So now what we're going to do is we're going to be using the table 7, very last row. So let's go to table 7, very last row. It tells me here that if I have P and Q, which implies R, I can replace, I can kind of distribute this implication. So I can put it in both parentheses and flip the and to be or. Now remember, in my case, my P, this thing is going to be actually not P. Q is Q, but then instead of R, we also have Q. So we will need to use R letters and not letters from here. So we're going to apply this through out here, table 7, last row, and we're going to have not P implies P. Sorry, not P implies we're distributing Q. Not P implies Q, or distributing the Q, Q implies Q. Double check, yes, yes, yes. Okay. Now, let's think about it. What can you tell me about Q implies Q? Yes, it's always true. Q always implies Q, correct? If it's sunny, then it's sunny, correct? Make perfect sense. It has to be always true. So what I can do is I can replace this with a true. So we have not P implies Q or true. Agreed? Now, how does the or works? What is the rule for or? So in order for or to be true, one of the sides has to be true, correct? But in this case, I have true on the right side, correct? So that means this whole thing always has to be true. Because something or true is always tautology, and we even have, I believe, this rule here. Where is this one? Yes. P or true is always true, domination law. So here we go. We figure it out. We showed this last thing is tautology. So now you have seen how you can use those tables in order to generate, to figure things out, to show logical equivalences, to show tautologies, and so on. However, I'm quite sure many of you are going to think that truth tables are better and quicker. Although sometimes truth tables might be pretty long, especially if you have multiple variables. So if you have like P, Q, R, T, and S, this is where you might try and want to play with logic rules. If I want you to do anything at all using those logic rule tables, I'm going to provide the tables on quiz or a test. So you're going to have like a piece of paper which is going to have all of those rules so that you can look at them to solve it. So there is no need to memorize it, okay? But you do need to understand how to use them. And this is something to play with because it gives you good a skill of, it's kind of again like a puzzle, trying to figure out what can I use from this table to make my whole expression simpler. Questions? You cannot skip steps. So no skipping. And it's going to be true for this whole class, because students think they can skip some things, they think those steps make sense or easy, and a lot of times this is where the mistakes are happening. So don't skip steps. Okay, so from section 1.3, your homework assignment is 6A. So actually, I believe everything else is already, okay, I did give you 8A, 12, BC, 18, 24, and 30, I believe, okay. So 6, I'm going to write it all, however, only part of it is due next Friday. So all of those are due this Friday. This one is going to be due Friday after, because we didn't study De Morgan rules before, and it's about De Morgan rules. Okay? And you already can see that 8A, 12 BC, 18, 24, and 30 are on the Friday's assignment. So it's no news to you. Okay. Section, oops. One 1.4. Okay, let's see. Eight A is not on the description of the homework 2, then it's going to be part of the next homework. So whatever was on homework 1, it was there. If I'm wrong, if it's not there, then it's not there. Okay, so let's. Then here we go. That's the correct way of doing it. Okay? Okay, great. Next. Here we go. So now we're in section 1.4 and we're going to talk about predicates and quantifiers. Okay. So statements that involves variables are generally not always true or false. So if you have a variable, like a mathematical equation, for example, for some values of this variable, the statement can be true. For others, it can be false, correct? It's not true that as here is a statement that has in variables and it's always true or always false, correct? So generally, it can take values either of being true or being false. So Generally, those statements will have two part variables and predicates. So let's look at what we got. So assume I have y less than equal -3. If I look at it and if I'll try to explain what's going on here, y is my variable, correct? And then I have this portion out here, which is called predicate. Kind of like a condition. And y is my variable. So what we can do is now we can create a so-called propositional function. Using those predicates, using like predicate is kind of like a condition, yes, is going to look like this. The P of y, the proposition using y, is going y less than equal 3. And now I can evaluate it. So I can say P of 2 is the same as saying 2 less than equal -3. And now it is a proposition. So now it is really always going to be either false or true. In this case, is it true or false? This is false, correct? Now, I can also do P of -10, for example. So now P of -10 means -10 less than equal -3. Is it true or false? True. So pretty much what we did here is we took a variable and a predicate together, and we generated a function where we said a propositional function is going to be this statement when I plug in different values instead of my variable, which kind of makes perfect sense because this is generally what you did with traditional mathematical functions. A lot of times in real life, we do have some preconditions and postconditions. Generally, precondition is information we have before an event have happened. So if you think about it with a connection to computer science, if you have, for example, a loop or something, and you know anything about variables as you enter, it can be method or function, this is going to be called precondition. And then postcondition is going to be information we have after the event. So in here, it's a good idea to kind of talk about pseudocodes. So we talked about conditions and we talked about propositions. So assume I have a statement saying if x is less than 5, then add 5 to x. So traditional statement, what I'm saying, if my x is less than, or actually, you know what, instead of if, I'm going to be using while. While x is less than 5, I'm going to add 5. And this is going to be going on. So that means I'm going to be repeatedly saying, checking. While x is less than 5, I'm going to add 5 to x, and I'm going to keep on going. Now let's talk about what preconditions we might have. So for precondition, I might state at the beginning something like, we start with x equal to 0. In this case, this is my precondition, this is my event. Now I want you to tell me what is going to be my postcondition. Oh my God, it is 10:25. Yes, the class is supposed to end. Sorry about that. I totally lost the track of my track. So anyway, postcondition, we are done. Postcondition here is going to be, for those who are interested, it's going to be x is bigger or equal to 5, and we are going to talk about it next time. Have a good day, and sorry about that.